Welcome everybody. My name is Alberto Marquez. In this video we will talk about the simulation inputs, and we will start with how to figure out representative distributions, and we will continue discussing how to generate random numbers, and finally how we transform the random numbers into the random variables that follow the representative distributions that we want. So first, let's talk about finding the best distribution. What we usually have is that we may have to go into the field and get samples of the process, maybe the time between arrivals or the processing times. Sometimes the information is available in the records of past performance and the operations of the system under study. But many times we will find that the data that we have does not follow the nature of the information that we need in order for us to actually have a good enough description of the behavior of the system in terms of the time of arrivals or processing times. And we will actually have to do a little bit of field studies pertaining to that. Once we have the data, then what we would like to do is to run some Goodnessoffit tests. And these Goodnessoffit tests, what they want to achieve is to compare the empirical data with theoretical distributions to see if some of them would be adequate to represent the behavior of that particular variable in the system. There are two very common Goodnessoffit tests we use. One is Chisquare and the other is called Magorov. We will see how these are computed. First, the Chisquare test. The Chisquare test compares the data observed against a theoretical probability density function. Basically what we have is that the number of data observed within a particular bracket in a histogram how would that compare to the probability of having that equivalent value in the theoretical distribution. The way that we do this is through a chi-square distribution. We have a chi-square tables, and what we would expect is that the summation of the errors that we find should be less than or equal to the threshold for the critical value in the chi-square distribution table. Usually we may have an alpha of 5% for this test. This is how we would do it. So the estimation of the comparison is done by computing some histogram of the actual observed values and comparing those observations to the expected value in the hypothetical distribution. Let's consider the following example. We have here a data stream of 877 points, and we can estimate some of the parameters that describe this data, including the number of points, the maximum value among those points, the minimum value, the average, the standard deviation, and we will consider 10 bins. We will create a histogram with all the bins will have the same probability of happening, and because we want to compare if this data is normally distributed, then even when the bins will have the same probability of happening, the bin width will be different. So first we define those equivalent probabilities. If there are 10 of them, each range should account for about 10%. So the limits, the upper limits for the probability associated to them are 10%, 20%, 30%, and so on. And the C value corresponding to 10%, 20%, 30% cumulative will be negative 1.28, negative 0.84, negative 0.52, and so on. In the limit, we cannot get all the way up to 100%, so we use 5 for the value of C. And then we estimate the value for the upper limit in the original data set. We use the C value for normalization. Now we start with the C value, and we can obtain the actual value of X. And X would be mu plus C times sigma. And the values that we obtain are 851.35, 893, 923.03, and so on. And then we proceed to count how many times we observed data in between negative infinity to 851, from 851 to 893, from 893 to 923.03, etc. And this frequency is the frequency observed. We have 99, 69, 90, 81, and so on. The number of values suspected in each one of these bins, since we expect to have 10% of the probability of the events there, because the bins were selected to have 10% probability, and we have a sample of 877, the expected value is 87.7. And with 87.7, we can compute our chi-square estimator as the square of the difference between the observed and the expected divided by the expected. And those values are computed in here under the column chi-square. And in our test, what we need to do is we need to add up all these values. The values are obtained, and the total number is 12.29, and the critical value in tables is 16.92. To understand a little better what we did with the bins, each one of the areas in the normal distribution depicted here in between the colorful lines are supposed to be 10% or approximately 10%. And in each one of these bins, we counted how many actual observations we had. We would expect them to be close to 10%. In this particular case, because we have 10 bins, the degrees of freedom that we need to use for comparison of the chi-square result is the chi-square with 9 degrees of freedom. And clearly the value that we obtain is in the non-rejection region. The value that we obtained was 12.29, and the critical value is 16.92, which is the region marked in red in this diagram. So we cannot say that the distribution is not normal. The way that I stated the words are very important, because the conclusion is not that it is normal. The conclusion is we cannot say it is not normal. We cannot make the full assertion that it is. We just have to be satisfied with the fact that we cannot say it is not. And why we take this type of decision? Because these distributions, and in every kind of experiment, this is not just for this situation, what would happen is that maybe more than one distribution could pass as a potential candidate the chi-square test. And if that's the case, it cannot be necessarily both normal distribution and some other distribution. And because of that, all that we can say is that we cannot reject the possibility of this being a normal distribution. And even that statement is under the assumption that we may have an error while we make the assertion. We are only testing for the possibility of not being normal, but since we cannot reject, we cannot conclude that it is normal. This concludes our example for the chi-square test, and we will see other goodness of fitness tests for the distributions in the future video.